Welcome to this explainer. I'm absolutely thrilled you're tuning in today because we're tackling something literally every mobile developer wrestles with at some point. We're talking about integrating serious machine learning muscle into your apps, but without turning your pristine codebase into this bloated, lagging mess. Today, we're going to lay out a complete chronological blueprint for building with Google's ML Kit. We'll look at everything from how you manage your foundational dependencies, to handling those incredibly frustrating GenAI setup errors, all the way to optimizing your final app size so your users aren't abandoning their downloads before they even start. If you're looking for a leaner, smarter application, you are absolutely in the right place.
Okay, let's dive right into our roadmap for today. We've got setup and dependencies, conquering common setup errors, feature availability and fallbacks, app size optimization, and finally we'll wrap up with dynamic feature modules.
All right, starting things off with Section 1, Setup and Dependencies. This is the foundation of the whole shebang.
So to lay the groundwork, you've got to configure your project-level build.gradle file to actually include the Google Maven repository, right? And then you add the specific ML Kit artifact dependencies to your app-level build file. But right out of the gate, you're faced with a major architectural trade-off. Do you go with bundled or unbundled models? If you bundle the models directly into your app package, the ML features are ready to rock the exact second the user opens the app, even if they're offline. But your initial download size, it's going to take a pretty big hit. On the flip side, unbundled models are delivered super thinly via Google Play services, so you get a tiny initial footprint, but the device might need a quick minute to download the model in the background the very first time the feature is called.
And you know, this brilliantly illustrates exactly why optimization matters so much. 800 kilobytes, that is literally the only size added to your app if you use the unbundled artifact for face detection via Play services. But if you chose the bundled version instead, you're looking at adding roughly 6.9 megabytes to your app size. Imagine multiplying that by 3 or 4 different ML Kit features. You can see how fast your app turns into a massive bloated download. That's the kind of thing that has users canceling the install before it even finishes, leaving you to deal with those brutal one-star reviews.
So you've set up your dependencies, you compile, you push it to a test device, and boom, you hit a wall, an error. This is especially true if you're working with the new GenAI APIs that leverage Gemini Nano. You're probably staring at the screen wondering, why on earth is AI Core failing to bind on a brand new device? It's an incredibly frustrating roadblock for sure. But believe it or not, it's completely normal behavior once you understand what's actually happening under the hood.
Which brings us to Section 2, Conquering Common Setup Errors, specifically dealing with those pesky AI Core binding issues.
All right, so here's the deal. ML Kit's generative AI relies super heavily on an Android system service called the AI Core app. It has to boot up and grab its configs from the server. When a device is fresh out of the box or maybe just recently reset, this process just takes time. Let's break down the logs you're inevitably going to see. Error code 601. That's a binding failure. This usually happens right after device setup. The fix is pretty simple. Just update the AI Core app and reinstall your app. Then there's error 606, feature not found. This basically means AI Core simply hasn't finished downloading its latest configurations over the internet yet. Just give it a little time or restart the device. Oh, and a totally critical note on 606. If you're testing on a device with an unlocked bootloader, you are always going to get this error. No way around it. The GenAI APIs strictly do not support unlocked bootloaders. And finally, error 0 is just an unknown download error. For that one, just make sure you keep the network connected, wait a beat, and retry.
Now, while we as developers see these resets and errors constantly during our own testing, your actual end users shouldn't ever see them. You've got to catch all these setup failures silently. Make absolutely sure you're calling check feature status or check status before you render any ML-related UI. If the model isn't ready, hide the feature, show a nice loading state. Whatever you do, absolutely never let the user see a raw binding failure crash on their screen.
Moving right along to Section 3, Feature Availability and Fallbacks.
Okay, so once the engine is actually up and running, the Prompt API lets you explicitly select your specific Gemini Nano model version by defining a model config. And you've basically got 2 distinct release stages to choose from here. On one side, you have model release stage.preview. You're going to use this during development to test out beta features and upcoming model architectures before they actually hit the general public. On the other side, there's model release stage.stable. And this targets the latest model version that is fully tested, hardened, and widely deployed out there on consumer devices. Let's see how this actually helps you build a more resilient app. Because preview models really aren't guaranteed to be on every single device out there, you need a rock-solid runtime verification checklist. Step 1. Initialize your generative model client with your preferred preview config. Step 2. You have to call check status to verify the device actually supports it. Seriously, the SDK won't just throw an exception on initialization, so this check is absolutely mandatory. And step 3, if that check returns false, gracefully revert your configuration back to model_release_stage.stable and model_preference.full. Doing this ensures your app is always going to work, entirely regardless of the user's specific hardware situation.
All right, let's shift gears to Section 4, app size optimization and cutting down on that APK bloat.
You know, your absolute first line of defense against bloated installations is simply how you package your app. You should always be building as an Android app bundle or AAB. When you upload an AAB, Google Play does this magic where it automatically generates highly optimized individual APKs based on a user-specific device. It targets their exact screen density, their exact CPU architecture, and even their specific languages. This means the user only downloads the specific native code libraries their device actually needs. They aren't stuck downloading this massive universal package that contains code for literally every phone on Earth.
Now here is a bit of a pro tip if you really need to push things further. You can actually manually shrink your APK by diving into your build files and explicitly excluding unused MLKit binaries. So MLKit ships with support for both 32-bit and 64-bit architectures right out of the box. But let's say your app relies on the third-party library that only provides 64-bit binaries. Well, your app is strictly 64-bit now anyway, right? So you can go in and explicitly exclude the 32-bit MLKit libraries from your packaging block. It is a manual configuration trick, yeah, but it strips out entirely unused deadweight from your final build.
And finally, we arrive at Section 5, Dynamic Feature Modules.
This right here is the ultimate optimization strategy for apps where MLKit capabilities are strictly optional. It basically involves refactoring your app to separate out your machine learning features and all their heavy dependencies into modules that are downloaded strictly on demand. Imagine, for example, you've got a note-taking app and it has this minor little feature for scanning document text using MLKit. Why would you force every single user to download those heavy machine learning models at install time if they might literally never use the scanning feature? With dynamic modules, they only download that model when they actually tap the scan button for the very first time. It's a total game changer.
But if you're going to implement this, there is one super specific, critical gotcha step that you cannot forget. In order for MLKit to function correctly within an on-demand module, you have got to go into your base APK's build.gradle file, meaning the base module, not the dynamic module, and explicitly include the MLKit Play Store Dynamic Feature Support Library dependency. It's a mouthful, I know, but it bridges the gap. It ensures the MLKit framework actually knows how to request and load these modules dynamically directly from Play services.
So the crucial takeaway here is this. Building with MLKit isn't just about calling the right APIs. It's like a giant puzzle. It's about architecture, bulletproof error handling, and rigorous optimization. Which leaves me with a final question for you to chew on. Have you audited your ML dependencies lately? Take the blueprint we just talked through today. Evaluate your bundled versus unbundled models. Implement robust fallbacks for GenAI, and definitely explore dynamic feature modules. You have the tools to make your app significantly smarter and leaner right now. Thanks so much for hanging out with me on this explainer, and happy coding!